Okay, time for us to do our problems. We're going to be doing problems which involve higher order derivatives and also doing some application type problems involving rates of change. So this is going to be some fun stuff. Of course, it's always fun stuff, but it's nice to start saying, hey, derivatives are good. Now, as always, to get the most out of this, you need to be doing as much as you can on your own first. So you should be using these videos as sort of an aid to sort of get a different perspective on problems, get some insight on what you should be looking for, and also to help you get unstuck. So if you're doing these problems with these videos, make use of that pause button and only do the video up to where you're stuck, get unstuck, and keep moving forward as much as you can on your own. If you do that, you're going to become really good. In fact, my hope is you get better than me, because that's the ultimate sign that I have succeeded as a teacher, when you can be better than I am. And I know you can do it because you're great. All right, well, let's get started on our problems. Find, or rather what is, the 10th derivative at 0 when our function looks like this: 2e to the x plus x to the 8th. And it asks some other question. What's the 8th derivative at 0? What's the 100th derivative at 0? Now you're probably thinking, we're really going to take 100 derivatives? Probably not. So when you see something like find the 100th derivative, we do not want to sit down and be like, all right, well, let's spend the next 2 weeks taking derivatives. What we want to do is start thinking pattern finding. So this problem is really as much about pattern finding as it is anything else. So let's start looking for those patterns. All right, so we have our function. G of x is 2e to the x plus x to the 8th. All right, now we'll start with our first derivative. And I'm just going to go ahead right away and just start using g. That notation means the first derivative. One derivative has occurred. Now, let's do our pieces. Derivative of 2e to the x. Well, the 2 is a constant, and the derivative of e to the x is e to the x. So it's 2e to the x. It didn't change. Now that's useful. Let's keep that in mind as we keep going forward. How about the derivative of x to the power 8? Well, the rule says bring the 8 down. X to the 1 less power. So x to the 7th. I was going to write 7 minus 1, but I just need to write 7. Okay, 8x to the 7. Now, second derivative. Okay, derivative of 2e to the x is, well, it's still 2e to the x. Right, good, 2e to the x. Now, here's where we're going to sort of test ourselves. What should we write down for the next derivative? Well, we know what's going to happen. There's an 8. Now the 7 is going to come down, x to the 6. Here's the question. What do we do with that 8 times 7? We can do one of two things. We can say, well, 8 times 7 is 8 times 7, or 8 times 7 is 56. Which way is better to write it? Now, the answer often depends on context. Now, so let's put it into our context. We're after patterns. When you're looking for patterns, it's better not to put numbers and mush them together, because as you mush numbers together, you lose context to where they came from. So we're going to leave it as 8 times 7. So that way we understand where the number came from. Now, if you wanted, of course, 8 times 7, 56. On a side note, 56, 8 times 7 equals 56 was always the hardest multiplication rule for me to remember when I was a little kid. I struggled with that one. So I'm glad that when I finally grew up, I was able to learn what 8 times 7 was. All right, the third derivative. And don't worry, we're not going to do too many more. We're just going to go until we see patterns. So what would that be? Well, the derivative of 2e to the x is still 2e to the x. In fact, it looks like whenever I take derivatives of 2e to the x, I'll always get 2e to the x. We found a pattern. Now this next part, what happens? Well, we bring the 6 down. Of course, the same question. Do we write it as 8 times 7 times 6, or do we write it as 336? Which one is more helpful? Well, 336, you hear it like, ah. But 8 times 7 times 6, you're like, oh, yeah, it's the number 8 times the number 7 times the number 6. I see that pattern. So that's why we say, yeah, it's not helpful sometimes to put everything together. Leave them as their pieces. And now we start to see what's happening. So let's go ahead and make things explicit. We know this part will always be the same. It doesn't change. Doesn't matter how many derivatives we take, it's always going to be 2 times e to the x. All right, so we know how to handle that part. It means it's always there. Now, let's think about the other part, and this is the more interesting part. What's happening here? Well, look at the power. I had to the 8, to the 7, to the 6, to the 5. So what happens is every time I take a derivative, the power goes down by 1. That should not be surprising. That's how derivatives operate. We always knock the power down by 1. So that tells us what the power of x is. And then, well, what's in front? Well, I had 8, then 8 times 7, then 8 times 7 times 6. Okay, good. So it's some product of numbers. So in fact, let's go ahead and jump ahead. Suppose we look at the 8th derivative of x. We can now see what should happen. We have 2e to the x, and then what comes next? Well, let's think of our power. We had 8, 7, 6, 5, and if you look, you can almost see it. The 0th derivative, which is just a function, and then here was 8. The first derivative, 7. Second derivative, 6. Third derivative, 5. So these two numbers always added up to 8. So if I've taken 8 derivatives, that means I'm up to x to the 0, also known as just a constant. What's the number? Well, it's 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 times x to the 0. But of course, x to 0 is just another fancy way of saying 1. Now, notice what we have here. This is a constant. Good. If I take the next derivative, what happens to that constant? Well, it's a big constant. Keep that in mind. And if you were to multiply it out, it would be 40,320. But even though it's a big constant, when you take a derivative, what happens? It goes away. It's gone. The derivative of a constant is 0. All right, so that says at the next stage, the 9th derivative, all that stuff, poof, vanishes to e to the x. Now, what happens next? Okay, after the 9th derivative, well, there's the 10th derivative, but we can see whenever you take the derivative of 2e to the x, you always get 2e to the x. It's always the same. In fact, this is always going to be the case. So what's the 100th derivative look like? Well, the 100th derivative will look like 2e to the x. Now we're ready to piece everything together. So our answers. The 10th derivative, we can spot it. The 10th derivative turns out at 0 when you plug it in. We're going to get 2e to 0, which is 2. The 100th derivative, same thing. So the 100th derivative at 0 is going to be 2 as well. And the 8th derivative at 0. In fact, in some sense, the 8th derivative of this function is the most interesting derivative because it's the one where it most stands out. You'll notice that in these derivatives that still have x to the power 1 or more, when I plug in 0, these terms disappear, and so I'm still getting 2. So if you look at derivatives at 0, it's like 2, 2, 2, 2, 2, 2, 2. And then at 8, it's all like, wah! And then back to 2, 2, 2, 2, 2. Now what's the wah? What does that turn out to be? Well, there's 2 plus this number, which I said was 40,320. I said that because it is, but that seems like a lot of work to write that down. So you might want to say, hey, this idea of multiplying 8 times 7 times 6 times 5 down to 1, is there a nice way to write that? And there is. This is known as a factorial. So the way you write it is as 8 with an exclamation mark. Now, it doesn't mean it's like 8, or you're going like 8, 8, 8, 8. No, that's not the factorial symbol. The exclamation mark is not somehow a form of excitement or a chant or anything. What it means is you start with 8, and then you multiply your way down, 7, 6, 5, down to 1. So this is a very convenient notation, especially the further you go. You're going to see this a lot, for example, towards the back end of your Calculus 2 adventures. So what's the 8th derivative turn out to be? Well, it's 2 plus 8 factorial. And that's the answer. All right, good, good. Okay, let's do another problem. So, given a circle with radius r, what is the rate of change of the area of the circle with respect to the radius for a given value of r? And a second question, how can this be interpreted geometrically? Okay, so let's think about our picture. So we have a circle of radius r. So let's imagine this is our circle of radius r. So imagine that's a reasonable circle. And as my drawings go, that's a pretty reasonable circle. And we have our radius. So here's our radius r. So we want to find what? The rate of change of the area of the circle with respect to the radius for a given value of r. Now you'll notice that there's really two pieces here. They are area and radius. So we're asking for how these things change in relationship to one another. So if I want to answer the question about how they change in relationship to one another, the first thing to do is ask, well, what's the relationship between these two quantities? So how are area and radius related as far as circles go? Well, there's a nice formula. It says that the area of a circle is pi times the radius of the circle squared. So we haven't started talking about rates of change. What we've started talking about is here's the relationship between these two quantities. Now, when I talk about rate of change equals derivative. And you can see, again, there's another key word here. There's this with respect to. So we can even read off what this says. If we're reading this sentence, the rate of change of the area of the circle, so that's asking for how is the area changing. So change in area with respect to over radius. So we're looking at change in radius, dr. So we're after that quantity. So we're taking the derivative of area with respect to r. So here's our relationship. So if I take the derivative of this with respect to r, so r being the variable, what would be the derivative? Well, you might say, are we okay to use r as a variable? And the answer is yes, we are perfectly okay. We can use any symbol that's convenient. And for us, in this particular problem, r is a very convenient symbol. So pi is a constant, and then the derivative of r squared with respect to r would be 2r. So we get 2 pi r. Okay, so that is our answer. Now there's a second part. How can this be interpreted geometrically? Now the way we think about the geometry is to think about how would it change if I just perturbed r a little bit? Because I'm asking the question, what's really changing as I change r? So if I were to push r out, what would happen is I'd get just a little tiny bit bigger. All right? So imagine as I move around here, if I increase r, I just push out ever so slightly. I push out and get a slightly larger circle. Okay? Very, very, very small extra piece. Now, the question is, what can we say about this slightly larger circle? What is it? Well, if you think about it, what we've done is we've just added a very small ring around the edge. So what we're changing is how much is there on the edge? Well, what is the edge of the circle? And the answer is that our change is the circumference. So the circumference is how far away it is to go all around a circle. And so when we change r, we're pushing out the area a little bit, and that extra area corresponds to roughly how much there was on the very edge of that circle. So that's the circumference. Okay, well that makes sense. That's a reasonable thing. Okay, well, that's a circle. Now you're probably thinking, I can see where he's going to go next. You're right. I'm going to talk about a sphere. So we're going to do a similar question. Given a sphere with radius r, what is the rate of change of the volume of the sphere with respect to the radius for a given value of r? Now, very similar question. So again, we can imagine we have our sphere. So let's say this is our sphere, and it's three-dimensional, so we'll give it a little bit of a ring around the center there. And here's our center, out some radius r. All right, so we have our nice three-dimensional sphere. And what's our question? Our question is, what's the rate of change? So that means the derivative. Volume, so volume with respect to radius. So that gets translated as, what is dV dr? So we start by saying, well, let's figure out what the relationship is between a volume and the radius. Now, for a sphere, we actually have the formula. And do you remember it? It's a nice little formula. It is that the volume of a sphere is equal to 4/3 pi r cubed. Okay, so that's the volume of a sphere, 4/3 pi r cubed. Now, take the derivative. We're taking the derivative. R is the variable. How do we know R is the variable? See this part downstairs? dr. That says r is what's changing, so r is the variable. 4/3 pi is a constant. Derivative of r cubed would be 3r squared. So you can bring the 3 down, and so the 3 will come down and cancel with a third, 4 pi r squared. Good. So that is the answer to the first question. There's a second question, though. All right, what's the second question? How can this be interpreted geometrically? So you have to imagine I'm just slightly changing r. So it's like I'm pushing out just a little bit. So I'm pushing my little sphere out. And the question is, how much is my sphere changing? What's happening to my sphere? Well, if I push it out just a little bit, what have I really pushed up against? Well, it's what's on the very edge, that very edge of the sphere. And what do we call that? What does it go by? Do you know? Well, what it is we've pushed it out, and this part right here is the surface area. So the amount of change is the surface area of the sphere. It's a fun fact. It turns out that it's true that the surface area of a sphere is 4 pi r squared. And so the amount that we are changing, the rate at which it changes, is the surface area, because that's if you push out a little bit, what you've created is this nice sort of this surface you've pushed out against. Okay. All right, good. Good. Well, let's do some physics. All right. The regional manager of a small paper company is giving a guest lecture at a business class and begins using miniature drones nicknamed Scott's Bots to throw candy bars into the audience. All right, well, I'm sure that will go great. The drones follow a strange trajectory with the height of a drone given by the height at time t, so h, height, that seems reasonable, minus 3t cubed minus 3/2 t squared plus 6t plus e cubed. The height at time t is measured in yards, and time, it has to be positive, is measured in seconds. The question, determine the acceleration of a drone at the time when the velocity is 0. Include units in your final answer. Now, one of the things I like to know is it says include units in your final answer. Oftentimes, if you are asked for units in your final answer, wait till the end to put the units in. Don't put them in at the start. Don't keep track of them. They're going to sort of obfuscate what's going on. We don't need to obfuscate any more than the problem already has been obfuscated. So, what do we have? Well, we have our height, so we'll start with our height. And notice a couple of things about this problem. We can see, first off, the function is pretty reasonable. That's good. We like it when it's something we can actually take derivatives of. All right, so minus 3t cubed minus 3 halves t squared plus 6t plus e cubed. Now I can tell that whoever wrote this problem put this e cubed in here as sort of a red herring, trying to trick us to make us think that there was something that was going to happen that doesn't actually happen. But, we're on to their tricks. We can see how they think. Why? What do we know about this e cubed? What's true about it? It's a constant. And so as far as derivatives go, when you take the derivative, what happens to it? It goes away. Good. All right. Now, let's point to some key phrases here. There's acceleration and velocity. Now, how do I know these are key phrases? They're italicized. That's a pretty good clue. But it also says, these have particular meanings. So, we want to find acceleration. That means we want to look at the second derivative when the velocity is 0. Now, velocity is 0 is a fancy way of saying this piece right here is a fancy way of saying h prime of t equals 0. See, velocity is h prime is equals 0. All right. So we want to start by saying let's take the derivative and set it equal to 0. So let's take our derivative. H prime of t. Derivative of minus 3t cubed. The fact that our variable here is t, no problems. So that becomes minus 9t squared. Derivative of minus 3 halves t squared. Okay, the 2 comes down. Minus 3t. Derivative of plus 6t plus 6. Derivative of e to the cubed. Remember? 0. So that's gone. Now, we're going to set this equal to 0. Okay, we'll do a little bit of work on the side here. Now, I can see that they're all multiples of 3. So let's get rid of a 3. So we can divide by 3. I want to actually divide by negative 3 just because I always like what's in front of my t squared to be positive. So this tells us we need 3t squared plus t minus 2 to equal 0. Okay, so that's what we're after. When is that true? Well, the next thing to do is see if we can get this to factor. Now, hopefully it factors, and almost everything will, so we have to think about it. Now, I'm not claiming that even though everything factors, that it's obvious how things factor. So we have things like we have the 3, and that breaks apart, or really only one possible way, 3t and t. And then we have things like the 2. Well, there's only 2 ways to do that. 1 and 2 are 2 and 1. See, if I put the 2 here, that would be a 6t and a t. Well, they're too far apart. That'll never work. So if there's any hope, it's got to go here and here. So the question is, what about the signs? Well, this will be a 3t. This will be a 2t. The fact that there's a minus means one of these needs to be positive, one of these needs to be negative. And when I combine the 3t and the 2t together, I need to end up with a positive t. So that should be a plus and a minus. So plus 3t minus 2t, and it all works out. Now, you can always go and check your factoring. You say, hey, 3t squared plus 3t minus 2t minus 2. In other words, you FOIL it out and see, do you get what you wanted? Okay. Now, let's see what that tells us. The fact that this equals 0 says one of these two things equals 0. See, that's this really cool property about 0. 0 is the only number with this property, which is why we like things equal to 0. And the property I'm referring to is if you have a bunch of stuff multiplying and the end result is 0, something had to be 0. So there's 2 candidates, either 2/3, and that's if 3t minus 2 equals 0, or negative 1. Now, which one do we pick? Or do we take both? So we look at our problem and ask if there's any way to eliminate an option. And there actually is. Do you see where the problem knocks one of them out? It's right here. At time greater than or equal to 0. Well, that rules out negative 1. We're moving past 0. So negative 1 won't work. So we say, aha, when the velocity is 0, happens at time 2/3. So, what are we looking for? Well, the acceleration is going to be h double prime. So our answer will be h double prime of 2/3. Because we figure out when is the velocity 0, we plug it into acceleration. All right, so here we go. Let's figure out what our acceleration is. H double prime of t. Derivative of minus 9t squared is minus 18t. Derivative of negative 3t, negative 3. Derivative of plus 6, 0. Good. So we're going to get minus 18 times 2/3 minus 3. So minus 18 times 2/3, well, 3 goes into 18, that's minus 6 times 2 is minus 12 minus 3, which is minus 15, which means it's going down quickly. All right, very quickly. How quickly? Well, what are our units? So we're after our second derivative, which means in the second derivative we take our units of our original function. Our original function is the height, and that's measured in yards. So minus 15 yards, divide by, in the second derivative we divide by the units of our input squared. What's our units of our input? Seconds. See, they even italicize things. It's like they want us to know things. So that's a helpful clue. Whoever wrote this, they're a very nice person. All right, so yards per second squared. So you might have thought it's meters per second squared. Well, no, because units can change. So don't just be like, oh, it's acceleration. It's always meters per second squared. Read the problem. Make sure you're adapting it to the right situation, because they know what you know. In fact, that's one of the hard things about taking calculus tests. Your instructor knows what you know. But see, now you know that they know what you know. Of course, on the other hand, they know that you know that they know what you know. You know, there's this sort of cyclical back and forth. It's a wonderful game. And of course, really, what happens is you just know how to do the problems. And then life is good. Life is good. All right, on to an application with economics. Okay, so here we go. Suppose that we have a cost function. So our cost for a given quantity Q is 30Q minus 22 times the square root of Q. And the revenue, the amount of money we get for a given Q, is 40Q minus 2/3 Q to the 3/2. So the questions, there's the marginal cost, marginal revenue, and where should we set production? And there's even another thing we have to do, which is answer the question, should we produce? Okay, so there's a lot to do. Now, the nice thing is we kind of understand what it means to talk about things like marginal cost and marginal revenue. So when we hear things like marginal cost, marginal revenue, what those are really referring to is what's the derivative of the cost and what's the derivative of revenue. So marginal cost, I'll write that as MC as an abbreviation. That's the derivative of cost. And so we say, well, what's the derivative? Well, first off, let's make a little note here of our cost function. See, that square root of Q, that's not a very calculus way to write that. We want to rewrite it in a nice calculus-friendly format. So 22Q to the 1/2 power. All right, so derivative would be 30. And now the next term, the 1/2 comes down, so minus 11. Then it's Q to the minus 1/2, because you subtract 1. Okay, so there's our marginal cost. How about our marginal revenue? Marginal revenue. What's that? Okay, we take our derivative. Derivative of 40Q is what? Well, it's 40. And then take this derivative. There's a minus, that'll still be minus, 2/3, and then we're going to bring the 3/2 down. Well, 2/3 times 3/2, perfect. We know how to deal with that. That just becomes 1. Then we have Q to the 1/2 power. All right, and so There we go. There we go. There's our marginal cost and marginal revenue. We've got two things figured out. Now the next question, at what point should we set production? So where do we figure out where to set production? The answer is we look at the marginal cost and marginal revenue, and they have to be equal. If they're not equal, there's incentive to change. So we have to take our functions and set them equal to each other. So 30 minus 11 q to the minus 1/2 should equal 40 minus q to the 1/2. All right, now I think it's safe to say we're going to assume q is positive. We can't take square roots of negatives, and if we have q equals 0, well, we don't even have any business. So it's a silly question. All right, so from now on, let's assume q is positive so we don't have to worry about any shenanigans with square roots. So we got to start gently massaging the equation. So what can we do? Well, let's move everything over to one side. So I'm going to move everything over to the left-hand side. So what would that say? Well, that would say q to the 1/2, then minus 10, and then we would have minus 11 q to the minus 1/2 is equal to 0. All right, cool. Or if you like, that's q to the 1/2 minus 10 minus 11 over q to the 1/2 equals 0. Now, at this point, you might start thinking, well, I'll just do some random guessing. Fingers crossed, I'll come up with the right answer, and life is good. But we're not going to do that. We're not about random guessing. Well, we are, but not today. Guessing is actually a really useful mathematical tool. I mean, shh, don't tell people I said that. But it's a true thing. Guessing, it can be a very powerful technique. So, if we're not guessing, what are we going to do? Well, what we will do is say, how can I rewrite this equation in a way that's more easy to use my tools? Now, oftentimes when I look at things like this, I say, can I possibly think of this as a quadratic? This doesn't feel very quadratic-y yet. Let's see if we can maybe get closer to it. Let's get rid of our fraction. I don't like fractions. They've always irked me. And I know I've made mistakes in the past with fractions, so I say to myself, let's not make mistakes again. So the way I'm going to get rid of this q to the 1/2 downstairs is I'm going to multiply everything by q to the 1/2. So when I do this first term, it'll be q to the 1/2 times q to the 1/2. So what we'll get is we'll have q to the 1/2 quantity squared. And I know what you're thinking, hey, that's q. It is. Hold that thought. What else do we have? Minus 10 q to the 1/2 minus 11 equals 0. Now, see what we have? Do you see something? See, what we can do is we can think of this as there is something squared minus 10 times something minus 11 equals 0, where the something happens to be called q to the 1/2. Temporarily, we're calling it a different name, so we can say, hey, now that looks an awful lot like a quadratic, because it is. Does that factor? Well, no surprise, it actually does. All right, can you see how that factors? Well, we need two things that multiply to get 11. Well, there's only one way to do that, 11 and 1. There's x and x. And what do we need? Well, we need to end up with a minus. So one of these is a plus and one of these is a minus. We also have to end up with minus 10x when we put them together. So I better make the minus attached to the 11. So there's minus 11x, and then there's a plus 1 positive x. So that way, if I put those together, I'll end up with minus 10x. So we have two possibilities, either x equals 11 or x equals negative 1. Now, we switch back, because x was just a temporary stand-in for what we were considering. It was a temporary stand-in for q to the 1/2. So that says q to the 1/2 equals 11, or q to the 1/2 has to equal negative 1. Now, one of these two we can eliminate right away without doing anything. Which one and why? The one we can eliminate is the q to the 1/2 equals -1. Now you might say, why can we eliminate that one? Well, when we talk about the square root of q, which is what q to the 1/2 is, we always mean the positive square root of q. This is a negative value, so we can't end up with a negative value coming out of the square root. So we only have q to the 1/2 equals 11, because that's a positive number, so that's fine. So that tells us what? Well, that tells us that we should pick q to be 11 squared. So q equals 11 squared equals 121. Now you might say, 121 what? Well, we don't actually know what we're making, so we'll just say 121 units. All right, so this is where we should set production. Okay, that's our answer to where should we set production. Now, one last question. Should we produce? Okay, so in essence what we've done is we found the, in some sense, optimal choice for a production level. The optimal level still may not be a good choice for us to do our production at. So how do we figure that out? Well, what we do is we quickly compute the cost. So we could say, well, what's the cost of making 121 units? So you would get 30 times 121 minus 22 times the square root of 121. What's the revenue of making 121 units? Well, that would be 40 times 121 minus 2/3 times 121 to the power 3/2. Now, at this point, you're probably thinking, this is a great time for a calculator. You are correct. Good. Good observation. Great observation. And I'll tell you, these are not pleasant numbers. So what you do is you take your revenue minus your cost at that level, whatever what it turns out to be, and you ask the question, is it positive or is it negative? And I'm going to go ahead and tell you the answer. It turns out that this is a positive value. I checked earlier. So what does that say? If it's positive, well, then hey, that says we should produce, because that means we're making more than it's costing us to make. So yes, we should definitely be producing. Good. All right, we're in business now. Woohoo! Time to start production. All right. Well, let's do one more problem. One last problem here. All right. So, Newton's first law states that an object in motion tends to stay in motion. So if I'm moving along, I'm going to keep moving along, unless, of course, I'm acted on by some outside force. So in particular, we're going to be our classic physics thing, that we're moving along, we're a vacuum, and there's a space, there's no gravity. So when I move along, how do I move? I move in a straight line. Okay. So what do we have? We have that there's a particle, and it's being moved along this curve, y equals 8 plus 4e to the x minus 7x for time x less than 0. So the particle, there's just some curve. I don't know what it's doing, but it's doing something. So here's this curve for time x less than 0. Then at time 0, all of a sudden, what's causing it to move along is detached. And so the particle is now doing what? It's not going to wiggle around anymore. What is it going to do? Well, it's just going to, if it was moving, it's going to stay moving. And it's going to keep moving in the way that it was currently moving at the time you let go. So it's going to move in a straight line. Now, which straight line? You could say, well, maybe it'll just start shooting off at some weird angle. That's not what particles do. They don't randomly fly off into some strange direction. Which direction is it going to go? Come on, think about it. Where is it going to go? Well, if you were to think about it in a calculus way, we would say, you can imagine that at time 0, you were to zoom in, and all right, let's do that. We have time 0. We zoom in, and what happens when you zoom in is that the curve it's coming off of looks like a straight line. And so what will happen is that the particle will say, you know, whatever this straight line behavior was at the time that you were coming in, I'm going to continue that straight line. So this particle will move along a straight line. Now, which straight line will it be? Well, it's going to be the line that the particle was behaving like. And in particular, that means it's going to follow along the tangent line. So that's how the particle will move. So I have this particle. Let's see, where's my particle? It's moving along, and then at time 0, it's going to go along a tangent line. Okay, so wherever this tangent line is, that's how it's going to move. And then it's going to come here and hit somewhere along the x-axis. The question is, where does it hit? That's what we want to find out. All right. So now that we have the idea, it's actually very straightforward to figure out what's going to happen. We need to find the tangent line and then figure out where the tangent line hits the axis. So let's start with the first problem. What's the tangent line? Well, if I'm after a tangent line, I need two things. I need to know where is the particle at, so I need a point, and what's the slope. Okay, so let's start with where the particle is at. We actually know where it'll be at, because at time 0, it's going to be at the end of where the force acts on. So what we'll do is we'll come into this expression, and we're going to say what happens at time 0. So you get 8 plus 4e to the 0, and then minus 7 times 0. Well, that's actually not so bad. So what do we have? 7 times 0 is 0. E to the 0 is 1. Come on, be careful. So you have 8 plus 4, which is 12. So right here, this is at 12. That's the y-intercept. What's the slope? Well, for the slope, we need the derivative, y prime. Derivative of 8, constant, goes away, 0. 4 is a constant times the derivative of e to the x, which is 4e to the x. Derivative of minus 7x, minus 7. Now, we need to know what the derivative is at the time 0, because we're after the tangent line at time 0. Y prime is 0, would be 4 times e to the 0, so that's 4 minus 7, which is negative 3. So our slope here of our tangent line is negative 3. Now we're ready to write down the formula for the line. In fact, it's going to be a really easy formula for us to write down, because what do we have? We have slope-intercept. So we can write down our formula, y equals negative 3x plus 12. Now, we found our line, so now we know, hey, this is how the particle is going to move. Where does it hit? Where's that point? Well, if we want to know where it hits the x-axis, what is the x-axis? The x-axis, you might say, well, it's the x-axis. The x-axis is the x-axis. But in particular, we can say the x-axis is where y equals 0. So it hits y equals 0. Now, so we say, okay, aha, that tells us plug 0 into here. So we need 0 to be negative 3x plus 12, or we need 3x to be 12, or we need x to be 4. And that is where we're going to hit the x-axis. As a point, we can write this as the point 4, 0. That's another way to express what we're after. All right, so now we did it. We're doing physics applications. Woohoo! Calculus is useful for something. Well, calculus is useful for many things. All right, thanks for joining and going along with the practice.